Okay, today we are diving into a paper that, honestly, is trying to reverse engineer scientific creativity itself. It's called Sci-Reasoning, a dataset decoding AI innovation patterns.
And it's so needed. It's looking past just, who cited whom and trying to map the actual cognitive process, the how and the why, behind a real AI breakthrough.
Their core contribution here is creating the first dataset that actually captures this structured intellectual synthesis for top-tier AI research. We're talking oral and spotlight papers from NeurIPS, ICML, and ICLR.
Right. And from that data set, they found these incredibly clear patterns. It turns out just 3 dominant strategies account for, what, over half of all these top papers?
52.7%, yeah.
Yeah.
Gap-driven reframing is the biggest at 24.2%, then cross-domain synthesis and representation shift.
And what's even more powerful is how they're combined. The most successful innovations use these recipes, like pairing that gap-driven reframing with a representation shift.
It provides this structured way of thinking that could train the next generation of AI research agents. It's a playbook, really.
It moves the conversation beyond a simple bibliography to the actual cognitive lineage of an idea.
Okay, let's unpack this a bit more. To start, let's talk about the problem they were trying to solve. Why isn't citation analysis enough?
Well, citation analysis is, it's easy to automate. That's its biggest strength. It tells you that a paper was influential.
But not how.
Exactly.
Yeah.
It completely misses the role of that influence. If I cite 5 papers, one could be a foundation I'm building on, another could be defining the exact limitation I'm trying to solve, and a third might be a method I'm borrowing from a totally different field. They're all just citations.
So Sci-Reasoning's goal was to convert that messy qualitative connection into structured data, to really map out the intellectual moves.
Yes. And the way they did it is almost as interesting as the findings themselves. Their methodology pipeline is really clever.
They start with a very strong signal for quality.
Right. A super strong signal. They just use the community's own judgment. If a paper got oral or spotlight status at one of these top conferences, it's high quality, period. No need to invent a new metric.
And the scope is just huge, 3,819 of these papers. So how do you process all that? How do you trust the data generation?
That's the key question. And they used an LLM-accelerated pipeline, but that's critical. It was human verified. So they used LLMs to process the full text and pull out that core story.
And which LLM did they use? Because I found this part fascinating.
They used GPT-5.
Wait, really? GPT-5, not something newer, like 5.2.
Yeah.
Kind of goes against the whole newer is always better assumption we all have.
It absolutely does, and they showed their work. The ablation study found that GPT-5 hit this perfect sweet spot of cost and quality for this very specific task. It had almost 90% recall, 89.73% to be precise, and actually did better than newer models on this kind of academic synthesis.
That's a great lesson in itself. So after the model extracts the info, it traces the lineage back, identifying 5 to 10 key predecessor papers.
Right, which acknowledges that breakthroughs are almost never a single bolt of lightning. They're a synthesis of multiple, sometimes competing ideas.
And that leads to the final output, these lineage graphs.
This is the gold mine. Everything is annotated. The role of the predecessor paper, was it a baseline, an inspiration? Did it identify the gap? And the relationship, does the new paper extend it, combine it, address its limitations?
But the real heart of it is the synthesis narrative, right? That little 200 to 400 word story.
That's the magic. It tells the intellectual journey. It explains how all those prior pieces came together to enable the new thing. And their main example, the Andes paper, just illustrates this perfectly.
Right, the paper on serving large language models.
It's such a great case study in synthesis. The starting point was, the standard high-throughput LLM serving systems, things like VLLM or SGLang. They were all about raw efficiency.
But they were optimizing for proxy metrics, like tokens per second.
Exactly. They were focused on throughput, on latency, SLOs. But that's not actually what a user feels. They weren't optimizing for the quality of the interaction over whole conversation.
So you could have high efficiency, but the user experience could feel, choppy or uneven.
Right. The real breakthrough they needed was a whole new metric, and that required a cross-domain insight.
And this is where they looked at video streaming.
Yeah, video ABR, adaptive bitrate. Think about how Netflix or YouTube works. Systems like Pensive or BOA, they don't just optimize for download speed, they optimize for a smooth picture. They have a formal idea of quality of experience, or QoE.
Which combines things like how long it takes to start up and how smooth the playback is.
And the Andes authors basically said, why aren't we doing this for LLM conversations? The user's QoE depends on how fast that first token appears and the smooth pace of the tokens that follow.
So they synthesized that QoE model from video streaming with a new architecture for LLMs.
A preemptive token scheduler. It didn't just push tokens out as fast as possible, it prioritized them based on the expected marginal QoE gain per unit of GPU time.
And the results were just incredible. A 4.7x improvement in QoE, or a 61% savings in GPU.
Yeah.
It's a perfect example. You identify a gap, you borrow a solution from a totally different domain, and you engineer them together.
And that kind of intellectual move is exactly what their formal taxonomy captures. The whole analysis boiled down all these moves into 15 canonical thinking patterns, actionable frameworks.
And like we said at the top, 3 of them are just completely dominant, making up over half the papers. Let's start with the biggest one.
P01, gap-driven reframing, that's at 24.2%.
Okay, so the cognitive strategy here is converting a failure or a bad assumption into an explicit design constraint. But isn't every paper trying to fill a gap? How is this different from just, improving the baseline?
That's a really sharp question, and the distinction is so important. Incremental improvement is when you just try to push a metric up a few points on an existing benchmark. Reframing is when you realize the failure isn't in your implementation, it's in the problem definition itself. You take a limitation and you make it a new design objective.
So instead of trying to make an existing architecture scale better, you'd ask, what if the architecture itself is the bottleneck?
Exactly. The example they give is with autoregressive image modeling. Instead of just trying to predict the next token faster, some researchers reframed the problem to predicting the next scale going from coarse to fine. They took the scalability limitation and made it a core part of their new architecture. It's a much deeper move.
Okay, that makes sense. Then the second one is the one we just saw with Andes. P02, cross-domain synthesis, at 18%.
And this is all about spotting an analogous problem in a field that might seem totally unrelated and then just mapping the solution over. The hard part is engineering that compatibility layer.
I thought the example of fusing quantum circuits with transformer attention was just mind-bending. Those fields feel like they're worlds apart.
They are. But the insight was recognizing a structural analogy between them. By mapping quantum concepts onto attention, they could create these doubly stochastic attention matrices. It's about realizing you don't always have to invent from scratch. Sometimes you just need to borrow and translate.
And the third one, P03, is representation shift and primitive recasting at 10.5%. This one feels a bit more technical, so let's break it down simply.
Okay, so representation shift is basically changing the fundamental language you use to describe the data. It's about swapping out the core primitives, the things the model actually sees, like pixels or tokens or meshes, for something new that makes the problem easier.
Can you give us a clear example of that?
Sure, think about 3D reconstruction. The classic way is to work with explicit polygon meshes, but those are clunky, they're computationally heavy, hard to optimize. A representation shift would be to move to something like neural implicit sign distance functions, or SDFs. Instead of a list of vertices, you have a continuous function that learns the shape. It fundamentally changes the math and makes optimization way, way simpler. That change in the primitive unlocks everything.
This is where it gets really powerful, though. It's not just about using one of these patterns. The best papers almost always combine them into what they call innovation recipes.
Absolutely. The #1 recipe with 318 occurrences is gap-driven reframing plus representation shift. They call it the reframe plus new primitive strategy.
And it just makes so much sense. You start by identifying a deep limitation, the reframe, and then you invent a new primitive that's specifically designed to make that newly framed problem easy. It's so elegant.
The second most common is cross-domain synthesis plus representation shift, the import plus adapt recipe. You borrow a cool mechanism from, say, robotics, and then you adapt its representation to fit neatly into your machine learning problem.
And number 3 is gap-driven reframing plus cross-domain synthesis, the diagnose plus barrow approach. That's the Andes paper. You diagnose a gap no one else sees, and then you proactively look for a solution in another field. It really does give you a meta pattern for success.
So now let's talk about the strategic implications here, because this is the stuff that's really crucial for any researcher listening who's thinking about their next project.
Right, like how these patterns have changed over time from 2023 to 2025.
Exactly. So gap-driven reframing stays pretty stable, around 24%. Diagnosis is always fundamental. But what's really interesting is the decline in formal experimental tightening.
That dropped quite a bit, from over 10% down to 6.6%.
Yeah, and that suggests that pure theoretical guarantees, while still important, are less likely to be the primary contribution of a top paper now. The field seems to be shifting the burden of novelty away from pure theory toward new representations and empirical results. And on the flip side, representation shift jumped up in 2024, and data and evaluation engineering grew in 2025. So finding new ways to encode data and building better benchmarks is where the momentum is.
It is, but even more practical than the time trends is the breakdown by conference. This is like the secret, whispered knowledge of the field, but now it's in a chart.
So you can actually tailor your submission. What are the different cultures of the conferences?
Well, ICML definitely favors mathematical rigor. You see more formal experimental tightening and principled probabilistic modeling there. If your paper has strong theoretical proofs, that's your target.
What about ICLR?
ICLR is all about architectural and empirical work. It loves representation shift and data and evaluation engineering. So if you've invented a new kind of token or a groundbreaking benchmark, ICLR is where you want to be.
And NeurIPS.
NeurIPS is the most balanced, but it has a slight preference for cross-domain synthesis, which makes sense given its focus on being a broad cross-disciplinary conference. Beyond just what's popular, the paper also points to what's unpopular, but in a good way. These underexplored opportunity spaces.
Yes, these are the patterns with low frequency but potentially massive impact. It's basically a map of where to dig for gold because not many people are looking there.
Like what?
Take multi-scale and hierarchical modeling. It's only at 1.5%. So many real-world systems are hierarchical, but our models often treat data as flat. There's a huge untapped potential there for more efficient and interpretable models.
Another one was adversary modeling and defensive repurposing at just 1.7%.
And with all the risks around large models, that feels like a critically underserved area. It's an urgent problem that, statistically, not enough top researchers are working on.
And finally, inference time control and guided sampling at 2.7%.
Right. Systems that can adapt on the fly at inference time, trade and compute for quality based on the situation. That's obviously critical for real-world value, but it's still a statistical rarity. These are the fertile grounds right now.
And really, the ultimate goal of this data set wasn't just for us humans. The whole point of Sci-Reasoning is to automate this process, right? To train AI research agents.
Exactly. And they put it to the test. They ran an LLM research ideation test. They took a NeurIPS 2025 oral paper, gave an LLM only its predecessors from the lineage graph, and asked it to predict the top 10 research ideas the final paper would propose.
How did it do? Could it actually mimic that creative leap?
The results were pretty amazing. Gemini 2.5 Pro got the best score with a hit at 10 accuracy of 49.35%.
So nearly half the time it predicted a research idea that was actually in a top-tier accepted paper just based on the inputs.
Yeah, it proves that the dataset is capturing real meaningful intellectual patterns, but the fact that it didn't get 100% is maybe the most important part.
That's the creativity ceiling.
Precisely. It validates that there's still a genuine, unpredictable stark of human creativity. The patterns are highly predictive, but that final novel leap, that's still where the magic happens. The LLM can follow the recipe, but it struggles to invent it from scratch.
So for now, the practical application is that these structured traces give AI agents explicit, labeled examples of high-impact reasoning. It helps them move from just summarizing papers to actually modeling the cognition behind them.
To wrap it all up, this work gives us a quantitative framework for innovation. It helps demystify the process, moving us past these vague anecdotal stories about genius and toward repeatable, measurable recipes for success.
So a final thought for anyone listening. If you're stuck on your next project, the data has a very clear suggestion. Forget just trying to improve the SOTA baseline by a point.
Don't just do that. Instead, try to execute the single most effective innovation recipe. Reframe plus represent.
Start with a really crisp, quantifiable, gap-driven reframing. Find that one fundamental mismatched assumption that everyone else is just accepting and working around. Diagnose it.
And then the second you have that diagnosis, you ask the most important question. If I could replace just one core primitive, the token, the mesh, the loss function, what would it be to make this newly framed problem trivial?
That's the trajectory. That's the structured path that this data suggests leads to a breakthrough.